Today, I will be presenting the findings from Lab 4, where we analyze the oscillations of a spring mass system. The aim of this experiment is to understand the motion of a mass suspended by a spring and to validate the energy conservation principle through both experimental and computational models. Let's dive in. The objective of this experiment is to examine a spring mass system's oscillatory motion and to compare experimental results with our computational model while checking for energy conservation. This experiment draws upon fundamental physical principles like Newton's second law and energy conservation. For the tools, we use Tracker software to analyze the experimental motion and GlowScript vPython to create a computational model of the oscillation and energy behavior. There are two key principles here. Newton's second law, which explains how the net force determines the acceleration of the mass, and the principle of energy conservation, which states that the total energy of the system remains nearly constant during oscillation, assuming negligible external forces. We also have useful equations for net force, kinetic energy, gravitational potential energy, and spring potential energy that form the foundation for our calculations. Let's move on to observing the actual motion of our spring mass system. What you see here is the analysis from Tracker showing how the mass moves in both X and Y directions over time. Using Tracker, we were able to accurately pinpoint the position of the mass at each frame, capturing its oscillatory path. These observations provide crucial initial conditions and give us a reference to compare against our computational model. One key takeaway is how the mass not only oscillates up and down, but also side to side, adding complexity to its movement that we need to factor into our model. In our computational model, the initial conditions are critically important because they set the stage for predicting how the system will behave. The mass of our object was estimated to be approximately 0.04 kilograms, as we're dealing with a lightweight origami object. Its initial position, derived from the Tracker software, is around -0.107, -0.632 meters, which essentially means it started in a slightly displaced state, not directly at the equilibrium point. We also assumed that the initial velocity was zero since the mass was initially at rest. This data is fundamental to setting up an accurate simulation in GlowScript, as small inaccuracies in initial conditions can lead to significant differences in the predicted motion. Here, we calculate the spring length and the various forms of energy in the system. The spring length is calculated from the mass's position and the origin, while the energies, kinetic, gravitational potential, and spring potential, are computed based on the system's motion. The total energy, which should remain roughly constant, is the sum of all these energies. Now, let's compare our computational model to the observed data. The experimental data, plotted in red, and the computational model, plotted in blue, reveal close alignment. However, there are some discrepancies. Two possible sources of error are the inaccuracies during manual tracking in the Tracker software and the presence of air resistance and friction that may have affected the oscillation. One of the core aspects of this experiment is to verify the energy conservation principle. The graph you see here shows the changes in different types of energy over time. The red line represents gravitational potential energy, the green shows spring potential energy, and the blue line represents kinetic energy. Notice how these energies fluctuate while the total energy, indicated by the orange line, remains nearly constant throughout. This indicates that energy is conserved within the system, despite the energy constantly changing forms. It's a powerful demonstration of the law of conservation of energy and highlights the consistency of physical laws even in simple experimental setups. In this slide, we compare the oscillation periods in the X and Y directions. We calculated the periods from the experimental data by averaging 3 complete cycles. The calculated periods in the X and Y directions are approximately 1.646 and 1.5197 seconds, respectively. The difference in periods might be due to factors such as measurement inaccuracies, non-ideal spring behavior, or external influences. To conclude, we successfully modeled the spring mass system using both experimental data and computational simulation. We observed that, while the model closely matched the experiment, there were some discrepancies that could be due to factors like air resistance or measurement inaccuracies. However, the energy conservation principle was well demonstrated in both the x and y directions, validating the reliability of our model. Thank you for your attention, and I am happy to take any questions.